This is Leetcode number 1, toSum, and it's should be pretty quick, but there are a couple subtleties, so I would think closely. So the question is, given an array, nums, so like this, and a target, return the indices of the two numbers so that they add up to the target. So for in this example right here, you would say 2 plus 7 equals 9. So we would return these indices, 0 and 1. In this example, we would say, okay, 2 and 4 they add up to the target 6, and so we would return those indices. And this is a good example because it shows that this list is not sorted. You would want to clarify that in an interview. And then this also touches on a subtlety. You may not use the same element twice. So you can't say 3 plus 3 here equals 6 unless it appears twice. So how would we solve this? Well, let's just think of a solution. I can think of a couple ones. So one would be to say we had 2, 7, 11, and 15. One would just be to say, okay, does 2 plus 7 equal 9? Yes, but say it didn't. Does 2 plus 11 equal the target? Does 2, 15? And then if that wasn't the case, we could compare every other combination. So here, 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 here. Oh, this is bad, but basically compare everything to everything else. You could make small optimizations. So like after you compared 2 to everything and you went from 7, you would only compare 7 forward. But regardless, this is still an O of n squared algorithm in constant space. So that's something. I would argue this is better than just saying a bunch of times and trying to go for a super optimized solution, because it shows you can get a solution. So how can we make it better? So I don't think we're going to improve on constant space. Usually the runtime is what is like what you would want to optimize. So how would we do that? So I would say that maybe instead of visiting, even just looking at our runtimes, what are the ones less than this? I would say, like n log n, log n, n, and these can actually give us hints as to like where actually we should be looking. I think that, there's going to be one solution. I think we're going to still have to look at every element because there might be we have to look at every value to potentially find the solution. So I don't think we can do it in O of log n. And O of n log n would require, it implies like a sort, maybe, or something to do with trees. So I'm going to shoot for O of n. So maybe 1 pass, maybe 2 passes, but let's just see. So this is our first solution. What are we actually doing when we are going through? So if you just look how you solve this with your brain, you're like, okay, you look at 2 and you say, okay, does 2 sum up to something? Does 2 plus something equal 9? And then you would say, okay, 7, you look in later, but say it wasn't. Say the target was 17, just for, we can go through the example. You would say, okay, 7, does something exist that adds to 17? Or sorry, to 17? It'd be 10, and you'd be looking at, okay, does this whole set contain 10? And so that's how you could go through. You could say, okay, we're going to go through each item once, and we're just going to see if the set contains the target minus whatever the current number is. And that would still be O of n squared runtime, but I think we're getting closer. This one is more intuitive to optimize because we're doing a search for each spot. And I think we can get better lookups than that. So say we're still searching for 9. What if we had a way to quickly look up things? This is where the data structure parts comes in. So if you dumped everything into a hash set, or let's just say a set with O of 1 lookup, then you would be able to easily do that computation. So you dump everything into a set. So that's your first pass. That's O of n because you're just, adding everything to the set. And as you go through on your second pass, you just see if the set contains target, so 9 minus whatever this current is, cur. And that's how you would be able to, that would be O of n. Because you're going through each element once, and each contains call is only O of 1. So let's go through that with another example. I'm going to try and crop. Oop, not crop. I'll figure this out later. So say we were, so what is the set? 3, 2, and 4. And then the target 6. Okay, so you dump those into the set. And then for each one, you just see if the set contains the target. So right here, you say, okay, 3 contains target minus cur. It does. 6 minus 3 is 3. It contains 3. So we would just return 0 and 0 as the indices. That actually violates, you may not use the same element twice. So this is a great example. So you might say, okay, crap, we're out of luck because it doesn't handle this edge case correctly. And I would say, what if instead of storing a set, we stored a mapping? So say this was our set right here. What if instead of just storing that, we actually stored the mapping of the index we last saw that thing at? So for 3, it would be at 0. And 2, it would be 1. And 4 would be 2. It's a great one. In this case, you could actually check. So as we go, we add everything to the map now. We say, okay, is 3 contained in the key set? Yes. Is the index we're currently looking at match this? Yes. Okay, then this is not a valid solution. We have to move on. So we can actually store that. So in the case, but let's go through this last case. So this is a case where it'd be multiple 3s, but we actually can return them as the answer. So what would our set look like? It would look like 3 at first. We would map it to 0, index 0. And then we'd actually overwrite that as we went to this next one. And we say, okay, actually it maps to 1. And we actually don't need to store everything. We only need to store the last one, really, the last mapping, or just any mapping that's not the first mapping. If we had multiple, even more 3s, we could store, in the third or whatever. But what's important is that whenever we're looking at this index, this one right here, that index is just different from this. And if so, that's a solution. We're good. So, our steps are put everything into a hash map, mapping the value to the last index. And then just iterate through. So let's write that in code. we have our map. So I will say our map of, and remember we're doing the value to the index. And we're going to do a hash map because we don't need any sort of ordering. And now we need to fill that up. So we're just going to go through for int I equals 0, I is less than nums.length. We're going to put in the map the value. So, you know, nums at I, the index. And then our last step was to iterate one more time. And just check if the map contains it. So if our map contains, or let's see, contains key, I think that's it. If it contains the key target minus nums at I, and I'm going to actually separate this out. So if it contains that, okay, we've hit one of these two cases. We need to do one more check. We need to say, okay, if I equals map.get at target minus nums at I. And if that's the case, that's this case right here. So I will actually say, in this case right here, we're just going to return, let's see, we're returning we're returning, how do you do this in Java? New int, I think it's something like this. And we're going to put in, let's see, we're putting in the indices. So I and map.get at target minus nums at I. And you know, for clarity, int target index equals, I'm just gonna separate that out. So yeah, and I mean, at the end, we technically don't need something. The compiler will complain if we ever reach here, even though we know we're guaranteed to have one solution. So let's just see, what it thinks of this. Incompatible. Oh yeah, we're returning, what is it, null in Java? So it likes that for the first case. Let's see if it handles the edge cases. Great. So that's 2-sum. Looks like we have 3-sum and 4-sum coming up, but yeah,